Hi, welcome to another MoTeC webinar. My name's Pete Swinney and this is our final part of our introduction to M1 diesel tuning. Well, that's the final part of our PowerPoint presentation version, at least anyway. Alright, so only one topic today, and that's our tuning workflow. So we're just going to go through the process of the workflow, the process that you would use to tune this diesel engine, the things you would cover and areas that you will go to. So let's get into it. Alright, research first. So we've spoken about it earlier, but if you do have the luxury of being able to measure and do a little bit of R&D on this particular vehicle that you're tuning, if it's not just an engine and a random boat or buggy or something like that, if it is a car that can be driven there and you can do some research, then it's a good idea to do so. I think the chances are that most of you listening today probably haven't tuned a diesel engine, depending on how many years from now that you are listening to it, of course. But it's very different from petrol tuning, as we've said all the way through. And so if you're well organized and are keen to learn properly, then I really do suggest you try and find out as much about how this engine would run in normal, with the factory ECU controlling it. So try and find out what is normal boost. With diesel engines there is a wide range of boost levels. Don't look at magazines or ask friends. We've been caught with that before. Physically, if you can't look at it on an OBD tool that you plug in, stick a gauge on it and see just what is the boost curve look like on it, and that'll give you a really good starting point for for your tune. You realistically could aim for anywhere from 14 to 35 pound. Some engines do have bigger turbos. They're running a lot more boost, right, even from the manufacturing side than others. So generally the range we see is 15 to 25 pound, like sort of in the 1 to 1.8 bar range. But yeah, if you don't know what the factory boost level is, then you don't know where you're going, and you're not going to know whether the power you're making is good or bad or otherwise. So as a general rule of thumb, if you match the OE boost and you run the engine with the right timing at a lambda of about 1.15, you should be making something like 10 to 20% more power, something like that. That's really rough figures. Most of the OEs are running quite a lot leaner, especially up at higher engine speeds, than what you can run once you've got control of the injectors. So they're fairly conservative for exhaust temp reasons and other things. So yeah, if you're nervous about the whole thing, then certainly do as much as you can. It's really good to see, if you can, see what their fuel mass is, see what their lambda is. Like, make it a project, put a lambda meter on it, and you can see what they're running. Just the more information you get here, the better. Now, also the turbo size. If this is an engine the customer's wanting double the output, no guys are going to take it to Dakar or going to take it on the track, then you might want to consider what the suitability of the factory turbo. And in most cases, certainly modern turbos in the 3-litre diesel ranges that we've been dealing with, the turbos themselves, as the years go on, are getting sized smaller and lighter and tend to be less useful for increasing particularly horsepower, not so much torque but horsepower, without damaging. So you really are on the limit of the turbo straight away in a lot of cases as soon as you run much more than the factory boost level. This is particularly true of the 1GD Toyota. As soon as you sneak above factory boosts at the upper end of the speed range, you're pretty much dicing with a high possibility of a turbo failure. So if straight away you're going to be wanting double the power, then you need to consider that the factory turbo is not going to be for you. So put some effort into finding what the right size is, and And it's not too far away from petrol tuning anyway, but yeah, better done at the beginning. Engine speed limit's the other one. You can't generally lift that a lot from factory. There'll be, I suppose, as time goes on, there'll be more people do more testing in that regard, because of the rotating mass weight of a diesel engine, the heavier rods and crank, then engine speeds are generally quite low, and generally the head, the efficiency of the airflow through the turbo, through the cylinder head, all of that is not really that wonderful at speeds much higher than the factory engine speed limits. But certainly that's something you want to consider, where you're going to run there, your gear ratios, everything revolves around that. But again, that's not too different to petrol. Before we get started, I think it's mentioned down lower anyway, I think it's a good idea often to drop as much as 800 to 1,000 off the max engine speed limit until you get on top of the tune. As far as damaging turbos goes, that all doesn't exclusively happen at high engine speeds, but that's when turbo speed is usually at its maximum, and that's when you're trying to run higher boost levels at those higher engine speeds. So just until you get on top of things, drop the engine speed limit, at least 500 below factory initially, just again until you get on top of it. Alright, so you've done your research and you're all prepared, so it's time to talk about what sensors you're going to put on this engine. Now, almost without almost exclusively, you always want a lambda sensor on. Now, you can actually tune without one on a diesel. A diesel actually doesn't have to run a particular air-fuel ratio, so you can do a reasonable job without lambda, but it's difficult to have any control of smoke. So the only time you'd ever consider tuning a diesel engine without a lambda sensor is if you really don't care about smoke. And having said that, if you don't care about smoke, that means you're probably running in smoke, and if you're running in the smoke zone with any sort of boost, then you're going to be in danger of high exhaust temps. So if you don't have a lambda sensor on it, at least have an exhaust temperature sensor on it, which is my second recommendation. But I think for most of you guys, it's pretty much an essential. You would have lambda. Exhaust temps, that next one. If you are going to be running on the richer side, then it's good to see what that temperature is, and sustained high exhaust temps over certainly over 900, 850 to 900 are probably going to cause variable nozzle turbo damage. Each engine's obviously different, so I can't give you a precise number, but you can't tune anything with any accuracy to any exhaust temp unless you measure it. The next two, it's one or the other. Well, not one or the other, but can't tell you which one's probably more important. Both are useful. Turbo speed obviously is, if you're concentrating on turbo development or are going to be at the limit of turbos you think that you've got to maintain, particularly if you've got to maintain for the rules the standard turbo, then you definitely want to run a turbo speed sensor. The limit of your power will be virtually smoke or turbo speed. Those two things will limit the power you'll make. So you can't keep adding fuel to the point of smoke, and you can't keep adding boost to the point of exceeding the turbo speed limit and blowing the turbo. Both can happen easily. A few taps on the keys and you'll be at either end very quickly. So the smoke you can obviously see. You can associate a lambda to a given level of smoke that you or the scrutineers or the flag marshals on the day consider to be the limit. You can then look at that as a particular lambda number and then make your tuning to that number, so that's why you would need lambda in that case. And your turbo speed, if you don't have a manufacturer recommendation of turbo speed and you blow enough turbos, you'll kind of get the idea of around what speed they expire. Obviously the smaller the turbo, the higher the speed. Already in my short diesel career, I've got rid of in the order of 5 or 6 turbos. So they are a bit of a consumable, and you are constantly at the limits of the turbo if you're getting the most out of your engine for performance. Exhaust back pressure is the other nice one to have. If you find that your mass flow via your airflow meter is dropping or not increasing proportionally as much as your boost is increasing, you can guess that the exhaust back pressure is the reason for that. It's nice to be able to measure it and see how bad it is. You'll be shocked when you see the numbers in the order of 6 bar with boost as low as 3 bar. The reason for those numbers is that because you have these variable nozzle turbos, if you're putting in a very low fuel mass and you want to make a high boost, so when I say a low fuel mass, if you're running the engine at what you call full power and you're running it as lean as, let's say, lambda 2, and you want to make a high boost value, then you will have to close the exhaust vanes very tight. When you do that, you get a very high exhaust back pressure. So that exhaust back pressure obviously affects airflow, affects power. So it's one of those sensors that I think is quite useful, and so if you've got the budget and the time, it's definitely one I'd recommend. And it's certainly really good to have there to log, and so that you can learn the behaviors of the turbo. It's quite nice actually also for the cost of running an exhaust temp after the turbo. So the exhaust temp you run will be before, and it's really interesting to see the difference between the exhaust temperature before and after, especially in relation to your vane position. As the vanes close and more energy is pumped and used by the turbo, you see a greater drop in exhaust temperature across the turbo. It'll change the way you think about EGTs measured after the turbo, that's for sure. So, I mean, realistically, the more sensors you can put on there, the better. It's really nice to have outlet pressure out of the compressor of the turbo. You can see surge happening there really easily, so that sensor would be mounted just right literally in the compressor housing. And if you're looking at that, a surge is reasonably easy to hear if you're on the dyno, but you can see it very simply. You'll see a big oscillation start in the manifold pressure or in that compressor outlet pressure. And you'll also keep an eye on your intercooler back pressure by seeing the boost on the turbo side versus the boost on the engine side. So and temperature before and after the intercooler as well is very nice. So it really depends on your project and your budget. The more you measure, the more you'll learn. So get it centered up and get it all working. Get your tune alarm set. So on the only picture we've got on our screen today is capture of some alarms I've got set up for a diesel project. I might flip to our Hilux here. So for those of you who don't know how to set up an alarm, it's quite simple, and anytime you're tuning anything, I would have, even a basic engine, I'd have some simple alarms set up so you don't have to concentrate on things like coolant temperature. So here's an example of a coolant temperature alarm, and you can just choose the channel you want for the package you're in. Double click it. So we've got on the list here, so I could delete this one, and why won't that delete? There we go. So we'll just redo this one here. So I can just search and go coolant temp. So here we go, coolant temperature greater than, in the case, that was the dyno, that's why it was so low. Our dyno runs about 85. So in a car you might be looking at about 105. You'd like to know what the temperature should be. So coolant temperature greater than, my cursor's not working. Why is that? Oh, I've got to enable it to enter the number. That's interesting. 105. So very simple. Coolant temperature greater than 105 Celsius. They'll get the tick to say that's okay, and then they'll go okay. So now whenever that condition is met, I'll get an alarm, and the name of my alarm is coolant temp. It'll just pop up on a screen. For those of you who have been tuning with M1, you'll have seen that. And you can even actually have it play a sound, and it'll actually tell you coolant temp. You can write all sorts of profanities on there if you really want. So quite a nice feature. Alright, so some of the ones related to diesel. turbo overspeed. So in this case, this was probably left over from the 1GD, oh no, from our 1KD. So in this case, whenever the turbo speed goes over 200,000, the alarm would come up and say, oh, I'm about to have to make a bad trip to see the boss and tell him I've blown another turbo. So we put an alarm on there to let me know when I'm doing it all wrong. Alright, so we've got a minimum lambda. That's another quite good one. If you're not watching the lambda, I think most of you would be used to doing that. Whenever my lambda, in this case, is less than 1.1 for 3 seconds, I'm definitely going to be smoking at that time, or very, very close to smoking. Maybe if it's just under 1.1, it mightn't be. Certainly any time it gets to lambda 1 or less than that, you can pretty much guarantee there's going to be plenty of smoke coming out. Alright, so I can set that up, and the alarm, it's actually a really good one. I really, just thinking about it, when you're getting used to tuning diesels, a lambda value of 0.95 probably wouldn't trigger you as being something being dramatically wrong. But if you're in a vehicle, can't see the tailpipe, then this will let you know that if that's your intention to stay smoke free, that currently you're not staying smoke free if this alarm is active. Okay, so I'd recommend you do that one. So, and the other quite nice one, I think I alluded to in a previous webinar, is fuel pump integral. And so this one is looking out for the fuel pump, your diesel high pressure fuel pump, being a little small. And that's actually quite common on a diesel engine because of the ability to make a significant amount more torque and power. Then it is quite common. One of the first things that you run into for a problem is if you run out of fuel pump. You don't run physically out of injectors. The injectors will always be able to deliver fuel, but they end up delivering it over a long period of time, so you end up with smoke issues. But it doesn't actually stop you tuning. Whereas the fuel pump, you'll literally run out of, get to the point where you run out of pump. And the way we can put an alarm for that is the integral, which is one of the PID components that effectively keeps fixing the error on the control based on time. So that integral can wind up. So if the integral in the case here is greater than 25, so it's having to add 25% more duty than normal to obtain the fuel pressure aim, that's really unusual. It should be within, realistically, 3 or 4, 5% duty should be enough variation from your feed forward point to keep the pump under control. The moment it's wound up to 25, it says, hey, you need to look at me, there's something going on. Alright, so things that as you get experienced you'll look at normally anyway, but when you're not experienced, all these things are going on. So take the time and set these alarms up, and they'll help let you know when things aren't ideal. When the fuel pressure is not being met, the pressure goes down, the pulse gets longer, and the engine keeps going. And often you won't know. You won't understand. It might lose some power. It might get some smokiness to it, but it'll keep going. And until you've got a lot of experience with recognizing the issues of what the engine runs like at lower fuel pressure, then it's pointless tuning when the fuel pressure is sitting down at 100 MPa instead of 200 MPa. So yeah, hopefully I've sold you on the idea that you should configure your alarms and keep on top of all of this stuff. Okay. Alright, so we've got our lower engine speed limit, sensible fuel mass limit numbers. Now, if you've got random injector calibrations and you really have no idea where you are with those, then I've got no real idea of what numbers to give you as a starting point. Generally, if your injector calibrations are within 10 or 15%, they're in the ballpark, something like that, then a fuel mass starting point, a maximum fuel mass of 50 milligrams, is going to be well under what you'll end up using. It's a nice safe number to start with, and you shouldn't end up doing any damage, over fueling or anything like that if we make that as a starting point. So what do I mean by fuel mass limit number less than 50? So we'll go back to, so you can start to see some of these tables. So we're in our, this is our Hilux package here, and we're on our tuning workbook, and our main, our fuel mass, or our first worksheet called fuel mass. So this has only got 2 tables on it. This isn't all the fuel mass tables. These are just the 2 common ones that you'll be spending time in. So this is the fuel mass limit, so I'll just click that to numbers. Alright, so what I'm saying here is here's the number we've ended up with on the Hilux, 140. I think you'll be somewhere south of 140 if the injector calibrations are right and you're making say up to double the amount of torque that the factory engine's got. Certainly around these numbers are right for a 3-litre style engine. So a number of 50 everywhere here. Let me save this as a new file. Save as, we'll call this training junk. Alright, so we get our random file, and if we want to make a start, I'm just going to type 50T. Alright, so what that means now, hopefully, if you've watched all the other webinars, is no matter what, I'll never get any more than 50 milligrams here. And that 50 milligrams is delivered proportional to our pedal. Alright, so here's our pedal, or our nominal. It's called the fuel mass nominal table. Alright, so basically it's a relatively linear, nothing at the bottom, everything at the top, what you'd expect for pedal. And we've got a big kick here, it's sort of an anti-stalling trend here. It's probably larger than it should be. I did it to prove a point with someone once. So yeah, if the engine speed ever slows down below 700, it just keeps adding fuel and it stops stalling. So that's a little excessive probably, but just going on that, if I can just quickly sidetrack, I can stop huge amounts of fuel being delivered at 700. How can I do that? I can make that number 10. So no matter what, at 500 revs, 700 revs, I can just carry on and put that side in here to prove a point. So at 700 revs, the way that's interpolated, no matter what, I can never get any more than 26 milligrams in. Alright, so if I was at 100% on our nominal table, even here down at 0 pedal, alright, then, so if I went foot flat at 700 revs, I'm going to get 100% of that number, 26 milligrams. And if all the other tables and limits and everything else in the ECU are all higher numbers than that, then 26 milligrams is what is going to be delivered, period. That's it. That's what you're getting. Alright, so that's our starting point for our fuel mass limit. Let's go back to the PowerPoint. Alright, so engine speed limit we talked about, tune alarms we've talked about, fuel pressure. Alright, so previous webinar we covered about fuel pressure, what you should do, the kind of reasons to do what you're going to do, considering hitting the piston, too high fuel pressure hitting the piston, but low fuel pressure makes for long pulses make for smoke. So generally we want as much fuel pressure as we can run without running into the dead time. If we're just considering performance, that's our overall guidelines. It's never that simple, of course, but that's where we're at. So let's have a look at the fuel pressure on this. So here's our Hilux fuel pressure, and so the more fuel mass we have going in and the more engine speed, the more fuel pressure we're running. Now you can see in here we've actually got quite a low fuel pressure at idle. That's probably lower than stock, and that is one of the previous webinars I alluded to why that is, and that's to help make the pulse width a little longer at idle and help us to run pilot pulses a little more easily without them skipping. So, and running the lower fuel pressure here actually quietens the engine down. The combustion noise is quieter as well. It makes quite a large difference. So I'm not saying you need to run that low. Between 30 and 40 at idle is the fuel mass, is the fuel pressure, around the fuel pressure you want to aim for at idle. Again, more fuel pressure at idle means that your pulse width would shorten and you might run into dead times. the dead time being the time it takes the injector to open. So if our calculated pulse width is less than the time it takes the injector to open, well, you just don't get any fuel. So that's your limit there. And then as we ramp in speed, engine speed and fuel, we ramp up fuel pressure. Alright, so we're quite conservative here. I think this system runs a maximum of 200 or 195 or something like that, I can't remember. So we've got 186 as a starting point. This is kind of our start file for the 1KD. And as fuel mass goes up, engine speed goes up, fuel pressure goes up. So that's a general curve of what you should be aiming for. Just note down here on overrun, down here when you're coming down off the throttle and your fuel mass is low, we definitely don't want high fuel pressure here because again, because there's so little fuel being delivered on overrun. So those lower fuel numbers, you need a low fuel pressure, so our pulse widths don't become too short. Alright, so that's our fuel pressure starting point, our fuel pressure aim starting point. Alright, our linear nominal, we just looked at that. Hopefully you can remember that. That's our pedal table. So it needs to be relatively linear. If you're on the engine dyno, you can make it completely linear because the shape of that table really is determined by the drivability, by how much power you want for any given pedal position. Shouldn't say throttle position because in a lot of cases there is no throttle. And even when the throttle is configured, virtually 95 or 99% of the time the engine is running, the throttle blade is open, so we're just letting all the air come in we can. Alright, so I don't know why I put that at that point. I'd probably put that at the end, but you want to start it and get the idle to work. Update these feed forward tables like I mentioned in the previous webinar for idle, the fuel mass minimum. But in most cases it should just start and idle straight away. There is a starting milligram point I probably haven't mentioned, so let me just show you that. You're not going to find that because that's not something you'll tune. I've put that down in our tuning setup. So we've got our same fuel mass worksheet under tuning setup, and in here is our fuel mass start. So while the engine speed is or the state is cranking, this is the amount of fuel mass that's being delivered. So don't try changing any other tables to add or subtract fuel while it's cranking. This is the only table that has effect while the engine state is cranking. Alright, okay, so while we're here, we'll just have a look at that fuel mass minimum table. Here it is. So this is where you will go to update the effectively the idle feed forward amount. So when the pedal is at 0, so your nominal table is at 0, this is the table that is being used. Alright, so it's also the starting point for idle control if you think about it. So when the driver comes off the pedal, we have 0% of the limit table and therefore all of the fuel mass minimum table. I wouldn't say this is a really good example of what that should look like, and you can, like I say, update this by looking at each coolant temperature and at each particular idle position. If you can check all these idle positions and what the correct fuel mass is to obtain those. Alright, so you can update that. Look, as I said previously, the idle control quickly fixes any errors anyway, but it's kind of nice to just keep chipping away at getting this right. Okay, so back to the PowerPoint. Alright, so that's our start and idle. Going through to make things, or to make it so that we don't get tables getting in our road or giving us results that we don't want while we get this thing initially set up. I suppose what our main aim on, if this is a fresh tune, is to come up with a fuel mass limit number that's sensible. So we want to end up with a fuel mass limit number, the number of milligrams of fuel that we're going to use as our maximum power number at all those different engine speed breakpoints. And so the last thing we want is, when we're trying to find those numbers, some of these other tables pulling the fuel out because they've got numbers that are lower than our fuel mass limit. So both the smoke and the lambda minimum, very similar tables in their operation. Both of those we want to put numbers that mean a large fuel mass. So in the smoke table, that's a large physical number, and the lambda minimum table, that's a rich number. So let me just quickly go and show you what that looks like. So back to my tuning workbook and off to smoke limiting. So the two tables are here. Just go to the smoke table first. Just press F6. We can make this go to full screen. Got some random numbers here. Now, as I said earlier, if our injector calibrations are in the ballpark, and this is approximately a 3-liter engine, then 3-liter across 4 cylinders, then we should be working with numbers somewhere south of 200 milligrams to make around double the power. Just to give you an idea of the numbers. So if I type a number of 1000 T in here, whoops, missed a 0 there, 1000 T for table, that means that virtually at no time should this table have any effect while we're getting this main limit table sorted. So just to go back on that, this table here, go F6 again, this is where we're initially heading. We want to really wind up our boost progressively, keep adding fuel, keep adding boost until we get to our maximum torque point for each of these. We don't have to get it exactly right on our first tuning session, but we want to be able to end up where I do a ramp run at max boost with the lambda at the correct point, and this be the table that is deriving the fuel mass. Alright, so that, and effectively this is about being the determining table that determines maximum torque that we'll get from this engine. Okay, so I'm not saying that you're going to know how many milligrams of fuel produces what torque and what torque this engine can stand physically or mechanically, but really this is the ultimate cap to the fuel, and fuel is realistically proportional to torque, provided you supply the air to match. So this is our max power fuel. Alright, so this is the table we want to get in shape first. Between this and boost, these are the two tables we're going to bounce backwards and forwards between. Alright, so we want to not have any other influences unless they're safety influences pulling the fuel out. So we lift our smoke table to a very high number, and just recapping here that the vertical axis of this is engine charge, which is airflow per cycle. It's not airflow per cycle, it's the actual weight, the physical charge of air going in, the physical mass of the air going in on a cycle by cycle basis. Alright, so that's there. Put this out for now. Smoke table, it's out of contention. Same for fuel mass minimum. Now this is how rich. If the computer, if we use this table, we're saying to the computer, based on the calculations that the ECU has for airflow and fuel flow, it comes up with lambda estimate channel. So what we're saying is, whatever the lambda estimate channel is, what's the minimum lambda estimate number that we want to accept at all these different breakpoints here. Alright, so here, now these numbers aren't always what you would expect, because if the calibrations aren't right, you might have a lambda estimate number reading 1.3 when the real lambda is reading 1.15. So if we want the real lambda reading 1.15 but the lambda estimate channel is reading 1.3, then we aim in this table for 1.3. Alright, but that's getting ahead. Right now, just so this table has no effect, we aim for something much richer, so that we're using, it doesn't become a limiting table. So that's, you go do that by 0.2t. Alright, so now the we want this table over here, this one here, our milligram table from our fuel mass limit main to be, this is the fuel we want delivered to the engine when we're at 100% pedal, and we want to see, is this too much fuel or is this too little fuel? We want to tune these numbers as our starting point to get our full power curve sorted. Everything that happens under that we can worry about with other tables. If we're not making boost at 2000 that we expect, we can use those other tables, the smoke table or the fuel mixture minimum table, to clip the fuel out if we're not making the air mass that we expect. But this table here is about if everything's going good, we're making maximum boost possible, this is the maximum fuel that we're going to allow. Alright, so sort those out, and yeah, that's relatively simple by comparison to the amount of time I spent. Last one, the boost. This actually the hardest out of all the tuning, I actually think, is getting the boost control right. It'll be the time where you spend probably the most time because of the complexities that a variable nozzle turbo and diesel both give you. So let's just quickly go through that. Back to the ECU. Alright, so off to our boost worksheet, and again, this isn't all of the boost setup. This is the common tables that you'd use for tuning once the engine's up and running. Alright, so a sensible boost aim is our first point. Now actually, when we're tuning the engine for the first time, we don't want to be aiming for too many different boost levels. This is the final boost aim for the Hilux engine. We'll just go to full screen. The reality is we want to just concentrate on aiming initially for one boost number and getting that correct. And we don't want to be aiming for that boost number at too low a fuel mass. If we have a very low fuel mass and we're trying to put even a moderate amount of boost in, then what will happen is that we'll have to close the vanes very, very tight, and you actually risk, even by closing them tight, you have two possibilities of things that will happen. One is that they close so tight that they restrict the exhaust flow, and the engine will actually slow down. You can get to the point where it won't even rev up on some engines because the vanes have so much movement in them, they can literally strangle the exhaust altogether. That's, some turbos do, some turbos don't, but aiming for a lot of boost when you don't have much fuel in there, that's one of the things that can happen. So a reasonable 40 milligrams actually isn't too bad. You should be able to make a reasonable amount of a boost, say half a bar. But realistically, to get on top of the boost control, we want to just aim for one set number and get that right. Now, if this isn't making sense to you, you should go back and review the webinar on boost control to kind of understand why that is. We're not going to get in depth into boost control in this webinar again. We will when we go onto the dyno. We'll go through it and you can see how it works. So if we'll make an assumption that this engine runs somewhere around 1 bar of boost in normal operation, I think a good starting point would be 80. And we're going to run, we had 50, so I suppose I should be sensible and put a 50 milligram side in here. So 50 milligrams, add that side in. Alright, so I've got a 50 milligram site here, and we'll put a target of 80 kPa. So remembering, of course, same as petrol, that this is gauge, so this is 0.8 bar, somewhere around 12 pound boost for old fashioned sake. And we won't pay too much attention initially down at 40 milligrams. Let's get to 50 milligrams, and we will concentrate on getting our feed forward table correct for an 80 kPa aim. So we might as well go to our feed forward table now. And have we got an 80 kPa aim here? No. So if I was starting from scratch here, I would go A for axis here, and I would have a single boost aim delete all that, and my single boost arm, I'll just put it there, 80. Okay. Oh, it's not going to let me. 0 and 80. Alright, so we're not worried about 0, we're just going to go straight to our 80. It'll interpolate when the aim goes below that, so we'll need to consider that. So now we have some feed forward numbers. There's no real way of predicting what they are going to need to be. We have a 50 site here, so once we actually start tuning and we get to our 50 milligrams, we need a row so that we're sitting consistently in one spot, and we'll end up sitting at something like 2050 milligrams, and we'll play with this number to achieve our 80 kPa aim. Now I know you can't see that there because of the color. There's probably not much I can do about that actually. I could change colors and that would take me all day, but anyway, so there's our 0. There you can see that now. That's our 0. So basically no boost feed forward table. We drop these right down. We might even start with it as 0T and our 80 milligrams. So you're effectively going to come in here once you get 50 milligrams of boost, as long as the lambda is somewhere between 1.2 and anything, then we're not overheat, we're not hot. And then if it over boosts more than 80 kPa when we first increase our fuel, we'll have to start making these numbers smaller. Okay, so that's effectively some sort of a setup. So I suppose if we wanted to be really safe, I could go Control A and 30 minus. Alright, so chances are when I come here at 2000 revs it won't make 80 kPa, and then I'll be able to bump that up. Now if you remember, we went through this in the one of the webinars about number 5 or number 4. That shape of our feed forward table is going to be high numbers at low fuel masses, and those numbers are going to go down as our fuel mass goes up, and as our engine speed, I've actually lost that shape since I've wiped 30 off it, but as our engine speed goes up, our numbers will go down as well. We'll open those veins more as the exhaust mass flow goes up. Right, that's enough on boost control. Little bits and pieces help along the way to get a grip of what to expect. And that's our basic setup, our tuning workflow, part 1 if you like. Just getting things set up. We haven't even turned the key yet really, other than idle. Alright, so the procedure now, which we've kind of covered, is basically we just start to add fuel. I mean, if you turn the key and everything's configured correctly, you can actually drive it right from the beginning, because you actually determine the amount of fuel with your pedal. So if you were in a vehicle on the road, basically turn the key, it should idle, and away you go. If you have got injector calibrations mammothly screwed up, and the thing smokes its head off when you put your foot down, well, take your foot off. If you take your foot to half the position, it'll probably ballpark half the fuel. So you'll get an idea straight away what to do with that max limit table, and you can tune it basically. You can get started initially, at least, just using the pedal as the fuel control. But the reality is that max limit table that we're tuning, we really only want to make an adjustment there after we've seen what's happening when our pedal is at 100%. So we're aiming to get our pedal, as soon as everything's stable, to 100% and see what happens. Now if you get to 100% and the lambda goes richer than lambda 1.2, then chances are one of two things: you've got the wrong numbers in the limit table, or it isn't making any boost. So if it's not making any boost, at that point we flip to the boost control and get it to make some boost. So at 2000 revs we should be able to get it very happily and easily on most, certainly standard turbos. It should easily make 0.8 bar of boost. So that's our next thing. So get to 0.8 bar of boost using your boost control. Get your foot flat and see at 0.8 bar of boost, and I have my pedal at 100%, I should be getting 80 milligrams, sorry, my apologies, 50 milligrams from our table. Let's go back to it. So if I do get my boost control at 80 kPa and I get my foot on the wood, well, then I should be getting 50 milligrams. At that point, you'll be able to look at the lambda and go, well, I can go richer because my lambda is currently 1.6. So at that point, bang in some fuel. So effectively, hold 2,000 either on the road or on the dyno and increase this number until our lambda maybe gets to lambda 1.15, 1.2. 1.2 is a good starting point. And then you might say, well, I want some more power. I'm looking at the dyno. The OE had a little bit more power than this, although that's unlikely. So if you want more power at 2,000, then and you're at lambda 1.1 with your new fuel milligram number, your limit. So let's say we get to 65 and we're at lambda 1.2 at 0.8 bar boost. Well, what do we do now? We go back and we make some more boost. So we go back to here, we go back to our boost aim, and now our boost aim, we might decide we're going to make 100. So we're going to aim for 1 bar now. We go to our feed forward main, and we're going to need to put in a 100 kPa boost aim sight. So A for axis, 100. Okay, and so now we concentrate on getting the feed forward numbers correct for 2,000 revs and our new fuel mass, which is 70 milligrams. Did I put in 70 or 60? Let's just check. 65. So if we're going to tune that properly, excuse me, we'll go and we'll actually put in that sight. So I'll make my fuel mass, instead of 60, I'll make it 65. So we'll hold, full pedal, 65 milligrams. The sight, active sight, will be here, 2,000 revs, and then we'll change this feed forward number to make sure we get our 1 bar of boost, our 100 kPa. So once we've done that, we might end up with a lambda of say 1.29, which means we can put some more fuel in. Alright, so I think you get it from there. So you can actually just bounce backwards and forwards, add fuel, then add the boost, then add the fuel, then add the boost, and keep going up. And so you'll get to a point where there's a few possibilities of where the end will be. The first one for us was the clutch started slipping. So we had to put another clutch in it, put a nice big tough clutch in it, because you effectively, at this point right now, you can keep bouncing your way back up and double the torque. You may get to the point you won't. It's unusual for you to damage the turbo at such a low engine speed, and the reason for that is that turbo speed is proportional. It increases dramatically based on engine speed. So if you have a turbo speed of, let's say, 60,000 RPM at 2,000 revs, at 4,000 revs, that's going to be something like 120,000 revs. I mean, I'm sure there's a better calculation than that, but turbo speed goes up on about a 30 to 40 degree increment proportional to engine speed at the same boost. I mean, that's a rough overview, but so if you take that information and think about it, what that means is we can make very, very large amounts of boost at low engine speeds, which is where very high torque numbers come from with diesels. So we can, realistically run twice as much boost safely at 2,000 as we do at 4,000. So at 4,000, to give you an example, on the 1KD, at 4,000 revs, our aim, I think, was 1 bar of boost. We're not aiming for 2 bar at 2,000, but I'm fairly confident if we did check that, if I aimed and went to 2 bar of boost at 2,000 revs, that our turbo speed would be still well in the safe zone. So turbo speed at these lower engine speeds isn't a concern. So what ends up becoming the limit? You end up with running. As the fuel mass is going up, you'll potentially end up running out of injector, running out of pump, or the turbo, as you want higher and higher boosts, will end up closing tighter and tighter to achieve those boost levels. the engine efficiency drops away, you have to close the turbo tighter and tighter, and then you get to the point where the exhaust back pressure is so high that you lift the boost but you can't get any more fuel in because the airflow is not going in. And while I'm ranting on about all of this, a really nice sensor that you can look at without a dyno, and it's almost as good as a dyno, and that is your airflow meter. If you've got an accurate airflow meter that's in range, then effectively if airflow is going up, torque is going up. And when you see the boost go up and the torque not go up, just look at the airflow meter and you'll see that that didn't go up either. Because as most of you know, if you've been tuning for a while, the engine's ability to make power is directly proportional to its ability to pass air. So if we don't get any more airflow increase, then realistically, unless we make it richer, we can't get any more power. Alright, so that's the rough overview of that. Now, and amongst all that chasing boost and fuel, we need to make sure that our fuel pressure is under control. So I'll show you that in detail once we go on the dyno. So you would be in a loop generally. You would go to fueling, then to boost, have a look at your fuel pressure control, then back to your fueling, get the fueling to get to lambda 1.2 and lift the boost, get the boost control sorted. That will lean the lambda out. Have a look at the fuel pressure control. Then once the lambda's leaner, you can add more fuel. Then you can go back to another level of boost. So you spiral round and round those things, and you'll be, if you haven't tuned a diesel, you'll be quite shocked at just how much torque can be made doing that process. Alright, let's see if I've got everything here. Backwards and forwards, use fuel limit, chase fuel pressure, watch power. We've got to be watching our exhaust temperature too. If we're staying, realistically, again, it's just a guideline, if we're staying leaner than 1.15, 1.2, exhaust temperature, certainly at those lower revs, should stay in control. You should be south of 750 Celsius. Alright, dial in the boost. We're pretty much done. Alright, so that's how you obtain max fuel. You obviously do that at all. That's how you obtain your maximum torque and your maximum power as you go up the engine speed range. But we haven't talked anything about smoke control. So again, we're just going on the process here, just the workflow of how you would tune. So if you're on a dyno, you'll have done that process that we went through for 2000 revs. You'll have done that at all engine speeds. You'll have spent a significant amount of time in the boost control section, and you'll end up with a fuel mass limit that's got a bit of a curve in it, because as you go higher and higher in the engine speed, it won't take as much fuel. So you'll end up with the maximum fuel and the maximum power that you're going to make. Alright, then from that point on, we would normally start looking at smoke control. So as we go and take this thing out on the road, there is plenty of occasions where it might not make that maximum boost that you tuned it with. But if you put your as it comes off the dyno, if you were to put the pedal to the floor, it would deliver the maximum amount of fuel from the engine mass limit table. But if the boost wasn't there and the airflow wasn't there, and if we haven't got either the smoke map configured or the fuel mixture minimum map configured, then when that lower airflow situation occurs, then the lambda will go rich and you'll smoke the neighbors in the street out without any doubt. So that may be a good thing in your suburb, but if it's not, then the next process and the next tuning thing to be working with is one of these two tables to control the smoke. Now, if your injector calibrations are even close to okay, then my personal recommendation is just to forget the smoke map, initially at least, and simply dial in the lambda estimate number that gives you the lambda actual number that gives you the smoke level that you're happy with. And it really is quite simple. and the ECU simply uses its internal calculations to derive the correct fuel mass to meet your lambda estimate aim via this fuel mixture minimum table. Alright, so you can actually, if you're on the dyno and you want to tune this, you can actually physically create no boost situations by opening the VNT turbo up, say at 2000 revs, open the VNT right up by overriding the boost control, aiming for a very low boost, go to 100% pedal, and then you will see no boost, all of that fuel going in that you have decided is the correct amount of fuel for high boost. Now you're still adding all that fuel, but there is no boost, and then you can tune this fuel mixture minimum table to say, hey, we haven't got any boost, but no matter what, we never want to be richer than this particular lambda. So just we've been in there enough times in the last few webinars, but if we're at our tuning workbook, we're going to our smoke limiting. If I had my way, I think we would just run this, just use this fuel mixture minimum table. Sometimes you need to use the fuel mass limit one because of injector cals just not giving you exactly what you need. But if we F6 this, so we've done our main power tuning, the engine's making really good power, customer's happy, sees a big number on the dyno, whatever. We're definitely, if the turbo's spooled up and our boost is running its aim, and we've got our good air fuel ratios, our lambda's good at all that time, we now need to concentrate on the times when we may come out of a corner, put our foot flat, the boost's not there, we need to limit the fuel at that point. So assuming we're at that part of the tuning, then a good starting point for this example, I'll assume that your injector calibrations are wonderful and that your lambda estimate is very close to your actual lambda. So if that was the case, and I never wanted it to go richer than 1.2 lambda at any time, I would go 1.2 T and we'd be done. And it would be literally as simple as that. And it's really good to see how this works. You'll see the lambda, you'll put your foot down, you see the boost isn't coming up quick enough, and you'll see the lambda and you're logging heading south, looks like it's on a path to go to lambda 0.8, and it'll just hit lambda 1.2 and go flatline. And realistically, that is, if you can get that situation where the calibrations are close, then this is just so simple. Now you might find that the lambda calibrations aren't quite right at some of these higher engine charge numbers, whether that be from the airflow meter or the injector cals, and you might find that lambda 1.2 is not, it's not quite lean enough, it's getting a bit smoky, so you can simply go